Hi, everyone. Thank you for looking at my poster. Let me quickly summarize it for you. Here I'm presenting the study of polarization configuration for the Farside array. Quick introduction. What does Farside stand for? Farside array for radio science investigations of the dark ages and exoplanets. This is a quick artist rendering of what the Farside plan looks like. There's going to be a base station. There is going to be rovers that will roll out tethers which contain our antennas. A few key parameters. The frequency range is going to be from 100 kilohertz to 40 megahertz. The antenna elements are going to be 100-meter dipoles, and a pair of them orthogonal to each other is going to make one antenna element, and there's going to be 128 pairs like this. Here I'm showing you the array configuration. Again, that's the base station at the center, and there's going to be a 4-armed spiral configuration. There's going to be a rover for each arm taking out the tethers in which the dipoles are embedded. So how it's going to be laid out is this quick schematics that I've shown you here. So there's going to be the tether from the antenna. The first dipole, X dipole, will be laid out. The rover will turn 90 degrees, then lay out the orthogonal Y dipole. And then the rover will take the tether and go on to the next antenna. Please note, the main important difference from any other interferometer we see on the ground is that the X and Y dipole are not face-centered at the same location, but they're going to be offset. Now, this is for ease of deployment, but these are going to have some effects in the images of the sky we make, and that's the effects I'm going to be studying. Now, understanding the effects quickly, here there's a diagram that explains that. In this, it's a co-located case. It's a 2-element array. Each element has 2 dipoles that are orthogonal to each other with the same phase center. So when the signal from the source comes in, there's going to be only one delay between these pairs that we have to deal with. And this is what we see in most of the arrays. But in the non-located, co-located case, the 2 dipoles that make the antenna pair is going to be offset. And in that case, in addition to the original delay, you will have an additional delay to take into account, and that leads into a couple of effects. One, it'll change the sensitivity of the array by changing the UV coverage. 2, it'll also cause intermixing of polarization components and polarization leakage, which is also what I'm studying. Why am I talking about polarization leakage so much? Why is it so important for the Farside? Simply because Farside's one of the main science cases is exoplanet studies. And for exoplanet study, we need the circular polarization information. This information will help us separate the host signal from the planet signal. And in any array, polarization leakage is caused by a lot of instrumental effects. In Farside, it's going to be a little more additional mixing of polarization because of this offset. So it's important we model and understand this effect so that we can maximize the performance of Farside. First, what I'm doing is understanding the effects of the beam because of the polarization, because of the offset. The procedure I'm following is presented in Cohn et al., and I'm using that procedure for the co-located and non-co-located case so that we can make that one-to-one comparisons. Now, the procedure involves taking the 2 beams, the X and Y beam, combining them or convolving them with the sky to produce pseudo-visibilities. I'm doing that for both. In the non-co-located case, I'm taking the beam and the offset term and convolving that with the sky. Then I go on to produce these polarization leakage maps that is shown by Stokes parameters. In each of these circles, the center is the horizon, the center is the zenith, and the circumference is the horizon. And the rows correspond to instrumental polarization, and columns correspond to what the sky polarization is. So in an ideal case, what we want is only what is in the green. That is, the diagonal terms is when you take the sky's I and put it into the instrument's I, you take the sky's Q and put it into the instrument's Q, and so on for the U and V. The off-diagonal terms are the leakages, which is what we don't want, but in any array, the beam effects itself causes leakages. And in the non-co-located case, the same leakages are there, but in the U and V case, the leakages becomes more compared to the co-located. And this is done for one frequency. These 2 plots are for one frequency. With increasing frequencies, the leakages becomes more prominent as shown in this plot. Again, the U and V is the last 2 rows. Again, by increasing the frequencies, your leakages become small. So now what does this mean for the actual sky? So the way I do that is I create a model sky with 3 A-team sources, the CAS A, Cygnus A, and the Sagittarius A. And I run it through a custom interferometer pipeline, which I've designed so that we can take into account the offset carefully. So what I'm doing here, I'm showing you in the pipeline here. So I take the sky for the 3 individual sources, those 3 different skies. I convolve it with the beam. I have the pseudo Stokes visibility as before, for, again, 3 different cases. Fourier transform it. I now take into account the UV coverage, which is the sensitivity of the array. So I take the array aspect into account and multiply that, inverse Fourier transform. I get individual images for the 3 sources. I phase rotate them, sum them, create a mosaic of the final image. And that's what I'm showing you in the plots here. The first column, again, it's no offset. Second column is with offset. And the last column is the differences between the 2. Again, these 3 individual points are the 3 sources that we expect. Now the sky has these 3 sources only in the I component. It's an unpolarized 3 sources. But the instrument tends to see these sources in Q, U, and V. Now for the no offset case, what we're interested in is the V to I ratio, right? The circular polarization is captured by V. The no offset case, the V to I ratio is not bad. Like it's 10 power minus 4 at 2 megahertz. But having the offset in place gives us the V to I ratio to 0.03, which is bad. And I've also analyzed the same thing for 0.6 megahertz. It's lesser compared to 2 megahertz, but still there. So again, this is reinforcing what we expected from the beam, that I and Q, we don't expect any changes. You see the differences are very low for the offset and non-offset case. You will expect differences in the U and V. The beam analysis told us we see that in the sky model too. So quick summary is that the Farside layout has offsets between the dipoles that make up the antenna element. This is so that it's easy to deploy, but this is going to affect certain aspects of the science of the array. It's going to change the UV coverage, basically the sensitivity of the array. It's going to change the PSF of the array, the eye, which we call the eye of the array, what the array can see. And it's also going to cause additional polarization leakages. We have constructed a formalization to study the offset effects, the beam offset effects on the polarized images of the sky. We've also constructed a complete pipeline where you can simulate point sources in the sky and look at the dirty images and see what the effects of with offset and without offset is. Now the goals are, we investigate. Yes, I'm telling you, there's going to be more leakage in V compared when you have the offset case, but we're investigating methods to calibrate the U and V so that it's not we can still do science with the array. I'm also assessing the polarized image performance of Farside. And finally, I also want to give a number to the Farside team as to what error we can tolerate when you place the dipoles, like in terms of orientation and in terms of distance. Thank you for stopping by my poster. Feel free to text me, email me if you have any more questions. Thank you.